In order to develop expressions for heat transfer from the flat plate, we need to develop correlations that are based upon the theory. These correlations, ones that we'll look at and ones that are in the book that are in addition to the ones that we will look at, all require us to have some knowledge or some defined methodology for determining the fluid properties. In these types of situations, we typically have a heated plate at T sub S, the surface temperature, and T sub infinity, which is the temperature of the free stream. So this temperature that we will use in most of our correlations is referred to as the film temperature. The film temperature is the average temperature within the boundary layer, where T sub S is the temperature of the surface and T sub infinity is the temperature of the free stream. So T sub F, the film temperature, is equal to Ts plus T infinity divided by 2. Now the fluid properties are tabulated in Appendix A, and they're tabulated as a function of the absolute temperature Kelvin. So since most problems are given to us in degrees C, it is extremely important to remember to convert from Celsius to Kelvin before taking a look at or developing or determining your tabulated values of your properties. So what we're looking at here is Appendix A, Table A4 is the thermal physical properties of gases. So we have air, and as we go down through it, we see that there's the gases ammonia, carbon dioxide, carbon monoxide are all available for us. So let's take a look at an example here. So if we have a surface temperature of 225 degrees C, the free stream temperature is being 29 degrees C, determine the average of those two and add 273 to it, we get a temperature value for the film temperature of 400 Kelvin. So if we go over to our table, we can go over here and highlight the row for temperature being 400. And now we can go ahead and bring our values over. So the density is kilograms per meter cubed. So we can just directly write this as 0.8711. So 0.8711. Now when we go over and we look at the specific heat, there's something different going on here because we again carefully look at the units, and the units are given to us in terms of kilojoules. Well, we would not typically use kilojoules, we would want to use joules. So we'll have to multiply this term by 1,000. So that becomes 1014 joules per kilogram Kelvin. Now going to the viscosity terms, we see the next four terms are all multiplied by some factor, in this case 10 to the 7, 10 to the 6, 10 to the 3, and 10 to the 6. What this means is that this value, 230.1, is 10 to the 7 times larger than the actual value. So what we need to do is we need to convert that. So 230.1, and we need to multiply that by 10 to the minus 7. And we need to do that for the other values as well. So the kinematic viscosity, 26.41, we have to multiply it by 10 to the minus 6. So 26.41 times 10 to the minus 6. Much the same for the thermal conductivity, though since it's only multiplied by 1,000, we'll typically write these values, in this case, as 0.0338. And for our thermal diffusivity, we're at 10 to the minus 6, so this value is 38.3 times 10. And the last value we have is for the Prandtl number, and this is 0.690. So the Prandtl number, a non-dimensional quantity, so it doesn't have its essential units. So we leave it as unitless. Just to quickly look at, most of our correlations are going to require a Prandtl number of at least 0.6. So if we look at air, we see that the value for the Prandtl number for air goes from 0.78, and it essentially goes down to 0.53. So it's only at 3,000 Kelvin that we would have to be careful about using our correlations. Same thing for ammonia, carbon dioxide, carbon monoxide, and the rest of our values. So we're pretty good at utilizing our correlations that we'll be developing. Now, if we need to, in the case here, say we were somewhere between 400 and 450, we would need to interpolate our value. So just in case you kind of forget how to do that, the temperature steps here are fairly uniform, going up by steps of 50. So if I was using a surface temperature of 260, a free stream temperature of 36, that would give me a film temperature of 421. So if I look at this, my K value at 400 is 0.0338. My K value at 450 is 0.0373. So my value that I want at 421, now you look at all of these values for thermal conductivity, they're always increasing. So I would take the existing value at 400, and to that I would add, well, 21, that's the 400 plus 21, divide that value by 50 because the interval is 50, and multiply that by the difference between the two of them. And that gives me my value of 0.03527 if I needed to utilize the thermal conductivity of air at 421 degrees.